and welcome to Tattva Deep, Conversations and Explorations. Our series of conversations on physics is now over. However, before moving on to our next subject, which will be biology, we'd like to share with you a compilation of insights shared by our guests on what they think physics to be. It's clear from their answers that physics is essentially a product of observation, measurement, repetition, and logic, while being an attempt to explain physical phenomena of our universe and even contemplate those phenomena that challenge our notions of space, time, matter, and causality. Although, in its details, the discipline is far from the affairs of everyday man, in its overall pursuit, it seems to be seeking answers to questions that are central to us as individuals and as a species. We'd like to thank our guests for being generous with their time and insights on Tattva Deep. With that, let's get straight to what they had to say about what physics is. Enjoy.
The question I've been asked is what physics is about. And that's a strange question, and in some way an open-ended question, because you might say, well, some physics now is about strings and string theory or fields or space-time, all kinds of things. But I think the most useful answer is to say that ultimately what physics is about, that is what it's trying to account for, is the motion of matter. Ultimately, what we want a physical theory to explain is why matter, material objects, move the way they do and form the configurations they do. And given that, physics needs to do several things. One is to give us an account of the nature of matter itself, and another is to give us an account of space-time, which is the arena in which the motion occurs. And then it depends on the theory. Then the theory may postulate new things, things we never thought of, like electromagnetic fields or strings or neutrinos. But it always does so in the service of getting a better account of the motion of matter. And that if we ever get a physics that gets the motion of matter entirely correct, as far as we can tell, that will be the end of physics. We will have achieved a physical theory that accomplishes what physics set out to do.
So I would say that physics is the study of sort of the most basic interactions in the universe, which if you really break things down to the sort of fundamental particle level, there are four ways that particles in the world interact with each other. Those are electromagnetism, gravity, and then the strong and weak nuclear interactions, right? And that's what holds all of matter together. The strong interaction holds the nuclei of atoms together. The weak plays some role in that. The electromagnetism holds atoms together, holds the electrons into the atoms and binds atoms into molecules and all larger structures. And then gravity is responsible for, holding large, planet scale kind of objects together. So pulling things in. So those are the four interactions. And then that's a very simple seeming system, but the consequences of that sort of spiral out and you get this increasing complexity as you go out. But fundamentally, physics is about taking relatively simple systems with just those handful of interactions and then looking at how everything plays out. And that covers a lot of scales. And sometimes we take sort of higher level abstractions of things we'll talk about. There's physics of materials where you're not talking about individual atoms, and worrying about the electromagnetic interactions between them, but you think about something like, a big pile of granular material, but that's acted on by gravity, and there are forces between the grains in that are still, it's a relatively simple system with only a few moving parts, but that gets you a lot of complexity in the end. This is sort of the distinction between physics and other sciences is largely a matter of where you make your sort of what level of abstraction you work at, right? So we talk about, atoms and the internal structure of atoms a lot in physics. In chemistry, they tend to talk about groups of atoms, right? You group them together into molecules, and then those molecules interact with each other at kind of a, one step up the ladder of abstraction. You talk about biology, then you're talking about, large groups of molecules that aggregate together to make cells and pieces of cells, and, lots of cells that aggregate to make organisms, and so on up the chain.
So what is physics? I would like to look back in history, and the first to use the term physics was Aristotle, meaning with this natural things. We are talking about things. So physics for Aristotle was the science about nature and things, the movement, the change, the motion, etc., and which he saw also having a goal-directedness, what he called a telos. Coming to our days, I'm not aware of a universally accepted rigorous definition of what really physics is supposed to mean and that everyone agrees on. However, starting from a more technical characterization, I would say that physics is a science that represents in forms of equations or differential equations the dynamical behavior of matter with the equation of motion of particles, or the energy state of systems, or the value of whatever physical quantity under the influence of forces, energy and fields in space and time, or space-time, taking the view of Einstein's general relativity. Deep down, at least at a microscopic level, all known physics could be reduced to four fundamental forces: the electromagnetic force, gravity, the weak and strong nuclear forces, plus space-time. That's all that physics is about. At the macroscopic level, it is also about the description of state functions. For example, in thermodynamics, one speaks of the state functions of a gas and its properties, such as pressure, volume, temperature, the famous entropy, and so on. So it is about a mathematical description of the states of objects subjected to forces and constrained by whatever boundary conditions and initial conditions. However, from a more philosophical perspective, in my opinion, these kind of technical representations of what physics is a bit unsatisfying. Because for me, at least, the question is, if physics describes nature and reality as it is, does it tell us what things are in themselves? What is matter? Fundamentally, ultimately. And what is space? What is time? Are these real objects or abstract objects? Is physics a science, a cognitive tool that gives us answers to ultimate realities and ultimate questions? Here, of course, we come into the domain of philosophy and eventually also metaphysics. But where the limits are between physics and metaphysics is notoriously not clear. There is no clear demarcation. In the philosophy of science, it is well known as a demarcation problem. That is the question of where science ends and metaphysics begins. What has to be considered science or what is pseudoscience, and so on. And that's why most physicists would tell you that it is not their business and not the business of science like physics to tell you anything that goes beyond the measurable empiric world, and they don't have to tell you about ultimate realities and what things are in themselves. But I personally can't refrain from asking myself deeper questions and believe that at the end of the story, our own human nature will force us to do so. There will be something in us that will almost force us to go back, at least from time to time, to tackle these deeply philosophical and existential questions. Then there is also this strange aspect of physics and how historically we see that physics is becoming increasingly, in a certain sense, immaterial, I would say even unphysical in a certain sense, so to speak. In the sense that we once had the idea of a perfectly deterministic universe made of particles, and that we thought of nice chunks of matter like marbles kicking each other around, following perfectly defined trajectories and so on, like in a perfect mechanistic clockwork. that, at least in principle, of which we could calculate past, present, and future state and dynamical evolution. This simplistic view has been shattered into pieces by quantum physics, where we have no such things as hard stuff and particles, at least not in the sense we would like to imagine as material solid objects having a precise position in space and time. And on the top of that, by the way, we have particles that can be in a quantum superposition of states or entangled with other particles at a distance and so on. That is, being in a physical state that has no longer anything to do with the kind of physicality and materiality, locality and determinism we experience from our, I would say, anthropocentric point of view and everyday experience. That's, by the way, also why I see critically all those attempts of interpretations of quantum mechanics that would like to save these aspects like locality and determinism in quantum physics. I see this as anthropocentric, an anthropocentric view and attempt to save our way, our humanly made way of seeing, perceiving, and conceiving reality, instead of accepting what reality is trying to tell us. Then you have in physics also this stuff which is not material at all. Massless fields like electromagnetic fields, gravity fields, nuclear forces that also have no materiality in the sense that are mediated by particles, massless particles, gluons so-called, and that's not material at all in the conventional sense. They are abstract spatial extensions we represent with mathematical functions as carrying forces, but they have no mass. And then we wonder what that strange dark matter is. We don't even know if it is matter at all, or the so-called dark energy, which makes it clear that we see and know of the universe, of a universe at best only 4 or 5% of the entire content of matter and the energy content of the universe, of the visible universe. We are only scratching a surface, and the more we scratch the surface, the more, so to speak, immaterial and unphysical gets physics itself. I'm playing a bit on words now, of course, but I hope you get what I mean. Physics is increasingly showing that our perception of the world is an illusion. Not in the sense that nothing exists, but in the sense that how we perceive the world is an illusion, an abstraction. And therefore I think it makes no sense to resist this fact, trying to bring back into physics our way of understanding reality. So I think that sooner or later a new science will have to emerge that will unite and integrate these two unavoidable needs of human nature that will not remain satisfied with a superficial understanding of reality. I love physics. It is no coincidence that I studied physics. But nurture no illusion that physics, at least this kind of science based on our human conventional reason, could be something that can ever answer ultimate questions about reality, matter, and our existence. It remains a very superficial description of what reality is. It is perhaps the best we can do now, today, but it remains a limited form of knowledge that is specific to the human mind. It is a science, the science of the Homo sapiens, specific to our species. In any case, of course, physics has also its practical side. It has given us machines, computers, electricity, and so on. But these more theoretical aspects of it are, after all, not much more than nice intellectual play for adults, I think. It makes us grow. It forms, disciplines, and develops the mind and the skills of the analytic reason. This is its real evolutionary purpose in the evolution of consciousness of humans.
That's a very, very large question that physicists and mathematicians have been debating over for a very long time. But I suppose if you put it ask a simple question of how and why, whatever answers those questions, I suppose that's the quest of physics. So physics attempts to answer the question of why something is happening, why a certain phenomena is happening, or how it's happening. If you have the famous Newtonian apple falling from the tree, why is it falling downwards? That's a why question. If you have, a ball rolling down a slope, how is that ball, moving in that manner? So that's a how question. And this applies to things at the macro level, at the very micro and subatomic level. Of course, I'm jumping quite ahead, but these questions are attempted by the community in general. And of course, one standard way of looking at it is that physics also looks at, observes. Observation is a very big word in physics, and measurement, of course. So if you can measure and replicate and observe, then we are supposedly in the right track. Having said that, I feel the whole realm of physics and what it encompasses is also in a state of flux. It's constantly changing. So that which cannot be replicated might also be in the realm of physics, and it might also be in the realm of philosophy, for example. And there's a lot of interaction, I think, between other areas, both of science and in general of life. Life's big questions, big philosophical questions, sometimes within the ambit of physics and vice versa. Physics is a catch-all phrase for a very, multifaceted discipline. We can't even call it one discipline. Certainly modern physics is super specialized. I suppose roughly you can subdivide it into 3 different realms. There's classical physics, what we call Newtonian physics. There's, and that's a whole realm. I suppose it's the realm of the macro, what we see, the laws of motion, a kind of Newtonian thinking that's based on Galilean thinking, kind of Descartesian framework. That's one realm of physics. Then there's quantum mechanics, which is another rough, very broad area, very important area. And then, of course, we also have relativity.
There's a few ways to answer the question, what is physics? I mean, if we consider its etymology, then it just means, from the Greek expression, it means knowledge of nature. And by this, then we need to define what nature is, and I suppose it would be something like the space, time, matter, causality, and the laws holding this whole system together. My preferred definition of physics, though, is due to a physicist turned philosopher known as James Cushing, and he defines physics to simply be what physicists do. And it changes quite a bit what physicists do, but ultimately that is what we mean by physics at any one time. So when a physicist goes to do a degree at a university, for example, I suppose they're not really told this is physics, this is not physics. What they do is they start learning a bunch of laws, learning a bunch of equations, learning how to do certain laboratory experiments and so on, and that is basically what physics is, and it might change at any point. There might be things added, there might be things taken away. There are controversial subjects that sit on the border of physics and non-physics. So the anthropic principle is an obvious example, where there are some physicists who think that it should belong in physics, and it's needed if you want to make sense of such things as why the constants of nature have the very specific, finely tuned values they do. Well, the idea is, if there is a multiverse of all possible values of those constants, then naturally we are going to find ourselves in a particular one of those which supports life, hence anthropic principle. But many physicists are not happy with that appearing as a valid explanation in physics, because you're not really building out from some more fundamental principles. There is also the question of whether physics is about reality or appearance. I suppose that goes back to whether what we mean by nature constitutes the full reality or whether it's the appearance. So I suppose Niels Bohr would be an example of somebody who thinks that physics is not the whole story, but instead it's a systematization of our experience of the world. So it's almost phenomenological view, where what matters is the relationships between our appearances of the world, and it's not necessarily telling us anything about the deeper reality of the world. And then the contrast with that is, of course, that physics is telling us about the deeper nature of reality. It's telling us about reality as it really is. I suppose Einstein would be somebody who defends something like that kind of view. Right? He wants to know what the world is like outside of the human mind. Niels Bohr didn't believe that that was possible, that you always have to put it within a frame, and it always has to be communicable in some sense, right, through classical language, so we can all agree on it. Not so for Einstein. My own view is more along the lines of Niels Bohr, I would say, that physics is an incredibly impressive tool for navigating experience. It allows us to make amazing predictions. It's clearly latching onto patterns, to real patterns, but it's not the whole story, and there's a whole deeper realm lying underneath. A lot of this has to do with the way we generate knowledge, which always involves a splitting of reality, I suppose, into an object system that you're analyzing and a subject that's doing the analyzing. And whenever you do this, you can never get outside of this relationship, right? So you've split up reality, and you are, because you're one of the observing systems within this dual pair, you are never able to step outside to check your theories of the world, to see whether they like that independently of your own frames of thought.
Physics is the business of modeling reality. The model is not the reality, but it's us trying to understand how reality works. So that fundamentally, in my mind, is what physics is about. Now, physics is required to be logical, because if you're going to model something, it needs to be a logical model. The model needs to make sense. It can't be just random models. It's better if there are fewer assumptions. There's a better model if there's fewer assumptions in the model. And it's a better model if it is simple and elegant as far as describing things that are fundamental. So there's many things in physics that aren't fundamental. They're just logical consequences. And sometimes deriving the logical consequences get very complex and very complicated. But the fundamental understanding of the nature of reality should be simple and elegant and logical. Okay, now, modeling reality has used the language of mathematics a lot. So we often think of physics as almost an applied mathematics, taking mathematics and applying it to describing what we call the real world, the actual physical world we see. But mathematics is not a defining component of physics. It's just a tool that physics uses. Logic is a defining component of physics or of science. We just talk in general, science. Because after all, physics is at the the logical bottom, the logical foundation of all the rest of the sciences. You start with physics. On top of physics is built chemistry, and on top of chemistry and physics is built biology. So physics is kind of the root. How does reality fundamentally work? And we make models of reality. It's important to know that the model is not the reality, and that models are to be judged solely on their ability to logically explain reality and how it works. And that model, like I say, should have as a few assumptions as possible and should be as simple and elegant as possible. So that's my basic look at physics. We physicists are about modeling reality, and the models need to be useful. They need to be able to make predictions and give explanations. We explain everything that we know. We should explain all the facts. Now, what makes a fact? In physics, a fact is something that is verified by an experiment, by multiple experiments, by multiple people in multiple places. And if you have that, then that defines a fact in science or in physics. Now, the experiment can be very simple. You can just pick up a rock and turn your hand over and the rock falls down. It always goes down. It never goes up. That could be a simple experiment. So that's what defines the facts. So we try to explain with our models all of the facts that we know, and we try to generate new facts, new understandings. So the theorists in physics say, well, I think if we did this experiment, we'd find this fact. And then the experimentalists in physics go out and do the experiment and see if indeed you do find that. So that's typically the way the science works. Sometimes it works the opposite. The experimentalists find something and say, wow, this doesn't make any sense. You theorists have any idea why it's like this? And then the theorists make up a story to try to describe why it's like that. So it can work both directions. But typically the theory leads. Then the experiments tend to try to justify or deny, the theory, whether the theory is right or not. Now, we in physics have given up, back not that long after Newton, or well, I shouldn't say that, in the early 20s, we gave up thinking that we knew everything. With Newton, we talked about Newton's laws. Then we realized that Newton's laws really weren't laws. They were only applicable to a subset of reality.
Right.
That part of reality that doesn't move too fast and isn't too small, or even too large for that matter. So it didn't apply everywhere. So they really weren't laws. And we kind of lost that arrogance then. And now everything is theory. So we talk about the quantum theory, relativity theory. We don't talk about the laws of quantum physics and the laws of relativity. Everything is theory. But in theory, we don't mean our best guess. We mean our best model, best logical model. It's a good question to ask because it's important to understand that these theories or models, and I use those words interchangeably. A theory and a model are pretty much the same thing. They don't have to be well liked. They don't have to even make sense. They just have to work. It's just important that they can deliver. They can explain. Matter of fact, as we have gone through multiple paradigm shifts, we realize that often the new, better theory that creates a paradigm shift, from the old theory, when that new theory came out, it sounded crazy, like relativity and quantum physics both. They sounded just a little goofy to the understanding that physicists had before. But then eventually they become mainstream.
Right.
But they start out as being strange, probably sounding wrong because they aren't explainable by the old paradigm. They kind of bust out of the old paradigm. So anyway, that's the nature of physics. It changes. It's not done. And new paradigms are in the wings, coming along.
Well, physics is basically the fundamental study of the dynamics of how events occur and the laws that produce those dynamics at all scales in the universe, from the small scale to the largest scale. So in that sense, it's of course subsumes chemistry and biology, which depend on the laws of physics to understand dynamics on different scales. But the fundamental dynamics and the laws governing them are what physics is all about. And that has lately, on the most fundamental scales, that's become an effort to try and understand what symmetries govern the mathematical equations that describe the world. My own approach varies. It depends. I try to stay closely coupled to experiment in one way or another. That hasn't been true for all my work, but I try to think about things that can be measured, or the implications of measurements. So if you look at my history of my work, and I have many different papers, some of it is based on surprising or important experimental results and interpreting them in terms of fundamental laws, and perhaps using them to probe for new fundamental laws of physics. And another part has been aimed at proposing experiments that could be used to test the fundamental laws of physics. And then some subset of my work has been, and that includes observations from cosmology as well as experiments here on Earth. That's how I, as a particle physicist, got into cosmology, because I thought the universe is a wonderful laboratory to test the ideas of particle physics. Mm-hmm. And the final bit of work, where the most esoteric parts of my work, have been looking at those fundamental laws and trying to understand the implications of those in a general way. So there's three-pronged approach of my own research.